With changing dimensions. Yesterday we were working with when you change the dimensions, what does that do to a two-dimensional object? How does it change the perimeter? How does it change its area? And so let's, we'll talk about that here in a little bit. Let's look at what today's learning objective is. Over here. I can determine the effect changing dimensions has on the volume of a three-dimensional object. So if we change the dimensions to either make a smaller or a larger three-dimensional object, how many times smaller, how many times bigger, volume-wise, does it get? Okay? So that's what we're going to be looking for today. So here we just have some review at the beginning here, and then we'll also add a little bit in that's not written on here. So when changing dimensions, it can be referred to as the scale factor. We talked about that yesterday. Or what did we say is another way they talk about it in the book? Ratio of corresponding sides. So let's fill that in. Typically, that's how they'll talk about it in the book. They'll say, how does the ratio of corresponding sides or corresponding dimensions change? Well, or compare, or whatever. You just need to let your brain go to scale factor. When they talk about ratio of corresponding sides or corresponding dimensions, they're talking about the scale factor. Let's be reminded, if a figure gets larger, the scale factor or the ratio of corresponding dimensions must be greater than 1. And we should always, when we're done, decide if that seemed what we got was reasonable according to this. If the figure gets smaller, the scale factor or ratio of dimensions, corresponding dimensions must be less than 1. And we even narrowed it down a little bit more than that. We said between 0 and 1, right? Because we don't talk about scale factors being negative. We don't have a 0 scale factor because then we eliminate the object. And we don't have a 1 scale factor if we want it to change. Otherwise, it would stay the same at 1. So yesterday, what did we learn with our two-dimensional objects? You have a scale factor, and to create your new object, your new two-dimensional object, let's say the scale factor is 1/2. What happens to the perimeter of the new object then? How does it change? It gets 1/2. The perimeter is 1/2 of the original one. If the dimensions change, they get multiplied by 1/2, then the perimeter gets multiplied by 1/2, basically. The perimeter of the old one changes by the same amount as the scale factor. How about area? What did we learn about area? What if the scale factor is 1/2, and how is the area affected then? Does the area get half as big? What does it get? 1/2 squared, which is what? What is 1/2 times 1/2? 1/4. So it gets 1/4 as big. Not just half as big, but 1/4 as big. It is a lot smaller. Okay, so now we're talking about three-dimensional objects. So when we're asked about the ratio of volumes, this is what we're focusing in on today. Let's put a box around that. Ratio of volumes. How do their volumes compare? They're really asking us for how many times larger or smaller does the figure get. Here's an example of a three-dimensional object. What's this called? This is a cube because it's a 3 by 3 by 3. So this is a 3 by 3 by 3 cube. Here's a three-dimensional object. If its dimensions are changed, basically we're saying how many of the volume of this changes by how much? How much smaller does it get, or how much bigger does it get? Okay, so let's take a look at this first one that we're practicing here. Every dimension of rectangular prism A. By the way, a cube is a rectangular prism, but it's a special rectangular prism where the length, the width, and the height that are all the same. But here we don't have a cube because it says every dimension of rectangular prism A, and notice what its dimensions are. We have a 5-inch, a 6-inch, and a 3-inch. It's a 5 by 6 by 3. They're doubled to form the new rectangular prism B. So what would the 5-inch dimension change to? 10-inch, okay? So this is going to be a 10-inch dimension now, and the new one. How about the 6 inch? What does that change to? 12. And how about the 3 inch? 6, okay. So the new rectangular prism called B has a 10 by 12 by 6 inch, that's its dimensions. So let's put that down here. Here's how we could show that as dimensions. 10 inch, we show times by 12 inch times or by 6 inches. 10 inches by 12 inches by 6 inches. So what is the ratio of corresponding dimensions? 2. And how do we know it's 2?
Because they told us how we got
Yeah, we doubled it. And remember, the ratio of corresponding dimensions is the same as the scale factor. So the ratio of corresponding dimensions is actually 2. Everything was doubled. And to prove that, we could say, well, if you put the new side 10 over the old side 5, what do you get? 2. That equals 2. Or maybe you want to do the 12 over the 6. What's that?
2.
2. Would that work for the third dimension? Yeah, it's going to work every time. The ratio of corresponding dimensions will be the same as the scale factor. Okay, so what is the volume of prism A? Anybody know how to find volume of prisms? No one?
length times width times height.
Length times width times height. So what are we going to do to find the volume of prism A? We're going to
5
take,
times 6 times 3.
okay, 5 times 6 times 3. And what are we going to say the volume is then?
90 inches cubed.
90 inches. 5 times 6 is 30. 30 times 3 is 90. And they were inches. Inches times inches times inches. Noah's right, it's inches cubed. So 90 inches cubed. Okay. Now you find the volume of prism B. Show your work. What do you have to do to get the answer? And then if you can do it in your head, do it in your head. If you can't, do it on your calculator. So show what's going in your calculator first on your paper. And then you can calculate it in the calculator if you need to. And don't forget to give a good label to it. And then see if you agree with me. Okay, did you get 720 inches cubed?
Yep.
Did that prism get bigger?
Yes.
Should it have?
Yes.
Okay. We doubled the dimensions. Does it look like the volume doubled?
No.
No. Does it look like the volume got 2 times 2 bigger than 4 times bigger? How can we figure out how many times bigger it got? Cody?
Because when you had your two-dimensional, you took the, when you had your scale factor was 2 by 2 equals 4, but now since we have a prism or a three-dimensional, and we have it doubled, so and it's cubed, so you take that you take the 2 by 2 by 2, which would be 6 or 8.
Which one is it? It'd be one or the other. 2
It'd be
times
8.
2 times 2 would be 8. So 8 times bigger. Okay, let's see. Remember what we can do to find out? Ratio of volumes. We would compare the new volume to the old volume. 720 over 90. You can divide that out. And what is it? 8. And so it looks like, Cody might be right. 2 times 2 times 2, it actually got 8 times bigger, okay, by doubling the dimensions. So that means 8 of the prism A would fit inside prism B. We could take that smaller prism A, our start, before its dimensions were doubled, we could put 8 of them inside prism B. Okay? Let me give you an example of that with a cube. Okay, here's a cube that, what would this cube's dimensions be?
1 by 1.
1 by 1 by 1. If you double those, its dimensions should be what?
2 by 2 by 2.
2 by 2 by 2. Does this look like a 2 by 2 by 2?
Yes.
2? Okay, so how many of these should fit inside this?
4.
I happen to have a couple of them, I don't have 4, but I want you to come up here to me, all of you, come, let's see. Do you think only 4 of those are gonna fit in there?
8.
8 of them. Go ahead, take a look at it, how many you said it'd only be 4? Okay, but will it be, can it really only be 4? How many would fit just on the bottom? 4. And then we still have another layer to put in there, don't we? So it's 8. So the same thing happening here. They got 8 times. This is actually 8 times bigger. Its volume is 8 times bigger than the volume of one of these. So, okay, we can have C. So, what do you think would happen then with this one? Let's predict what would happen with this one. What did I do to the dimensions of this one compared to this one? It's a 3 by 3 by 3 cube. So how many of these do you think would fit in this one, in the new 3 by 3 by 3? We got a 1 by 1 by 1 and a 3 by 3 by 3. How many of these do you think are going to fit?
27.
27. How did you get 27, Noah?
Well, we took, on the other one there was 4 on the bottom, and there's 9 on them, and there's 9, so I just took 9 times 3.
Okay, so in other words, 3 times 3 times 3, right? The scale factor is 3. So if you take the scale factor times itself 3 times, you have 3 factors of the scale factor, and that is how many would fit in here. 9 on the bottom, 9 in the middle layer, 9 on the top layer. So 9 times 3 is 27. How do we get 9?
3 times 3.
3 times 3. So we took the scale factor as a factor 3 times. So what happens is, how does the ratio of the volumes relate to the ratio of the corresponding dimensions? What are we going to say there? How does it relate? 8 is what? We found the ratio of the volumes to be 8. 8 is
2 times 2 times 2.
Yeah, you guys said that earlier. You said it's 2 times 2 times 2. So what are we going to say? The ratio of the volumes is the scale factor cubed. Take the scale factor times itself 3 times. Ratio of the volumes is the scale factor. I got to get the word "the" on there. Sorry, I missed it. Is the scale factor cubed. So, knowing that now, do you think we could have found the ratio of the volumes without finding the volume of each? Okay. Not going through all that work and having to find the volumes. Did we, when we were just here now talking about this 3 by 3 by 3 compared to the 1 by 1 by 1, we said that the scale factor is what again? 3. Did we worry about finding the volume of either of them? No, we said that they would go in there 3 times 3 times 3, the scale factor cubed. 3 times 3 times 3, we said 27 of these should fit in there. And if I had 27 of them, you could prove that it actually does. So, we do not need to know the volumes of each. What do we need to know?
The scale factor.
We need to know the scale factor. So we'll say if, we'll put a comma there instead of a period, if we know the scale factor, we could find that ratio of volumes. We could say the ratio of volumes. We could find it without even knowing what the volumes are. We could say the ratio of volumes is the scale factor cubed, what we set up above in number 6. Okay, let's go to the back then and practice some problems like are going to be new types that'll be on your worksheet today. You'll have some on your worksheet today that'll be like yesterday's, and then you'll have some that deal with volume like these do, okay? So number 8, we have this cube that has a side length of 4 inches, a scale factor of 2 is applied to the cube to form a new cube. Is that new cube gonna be bigger or smaller? Scale factor of 2.
It's gonna be bigger.
Gotta be bigger because it's got a scale factor greater than 1. How many of the original cubes would fit inside the new cube? Do we need to make the cube that that's a 4 by 4 by 4, and then double it and make one that has an 8 by 8 by 8? Or can we find this without that?
We can probably without.
Okay, what are we gonna do?
If we take the 4 inches and find if we can fit 8 inside, we can take that times 2.
We can fit 8 inside, and we can take that times 2. Not sure what you mean, though. Try that, let me at that at a different angle, see if I can understand what you're trying to say to me.
Like what we were doing with that 4 by 4. If
Okay.
we can fit 8, we can.
So you think there would be, if we double the size, there would be 8 of them that would fit on the bottom of the new one? 8 of the old would fit on the bottom of the new?
Yeah.
Okay, and then how many layers would there be?
No, 8.
Okay, so there'd be 8 layers. Okay, so then so that there's 8 layers of 8, how many would fit in there?
64.
Okay, no, I think 64 would fit in there. How about anybody else? You guys want to agree with me? I think 64 of the 4 by 4 by 4 would fit inside the 8 by 8 by 8 after we've doubled the dimension. Sorry, you know, nobody agrees with you. I don't know. Sure. I don't know why, but. So, what do you think, Julie? Because it's the scale factor cubed. How many, so what would that be? 2 times 2 times 2 is 8. So you're saying, Julia, that 8 of them would fit. 8 of the old would fit inside the new. Okay, how many of you agree with Julia? You think the same thing. You think 8 of the old cube, the 4 by 4 by 4, would fit inside the new cube, which is an 8 by 8 by 8. So, a couple of 8 people are going to agree with you. Somebody else, Cody.
Well, 8 times 8 times 8 would be, it'd be 3,728, I think.
That's too big of a number.
It is. Why are you taking
I mean-
8 times 8 times 8, Cody? What's the reason?
Because it's, a 3-dimensional, because it says a cube has a size of 4 inches, and the scale factor is 2, so wouldn't you just multiply 8 by 8 by 8 to get that volume, and then you put, then you divide it by 4 to get your answer?
So this is a 4 by 4 by 4. Can you guys draw cubes? Go ahead, try it. And then if we double the side lengths, we get an 8 by 8 by 8. So what you were doing, Cody, is you said, I'm going to take 8 times 8 times 8. Why?
Because then you get your volume, and then you divide it by 4.
Why would you divide by 4?
Because you have a 4 by 4 by 4.
So you're just going to divide by 4 the side length of it. So you're going to put the volume of the new one over the side length of the old one. Is that what we should do?
No.
Jossie?
Do you know this? Yeah.
So to decide here, what do you think we should do? So I like that, you know, you want to find the volume of the cube. So maybe we should just do that then. 8 volume equals 8 times 8 times 8. So what is the volume of this big cube?
512.
512. Okay, much smaller number than your first time, huh? Okay. And then these are what? What's the label on there?
Units, or inches.
Inches.
Or cube.
Cubed, okay. And then this one's volume we would get by doing what?
Same thing.
4 by 4 by 4, which is
64.
64. And those are inches cubed?
Yep.
Okay. Now, how is that useful to us?
Because you divide 500, you divide the new one by the old one.
Okay, so we're going to set up the ratio of volumes, is what you're saying then. This is the ratio of volumes that we're going to set up. New over old. Ratio of volumes, new over old. So what is 512 over 64?
8 inches squared.
Okay, but
Or
now
8 inches cubed.
the inches cubed cancel each other out. It's just an 8. It's a ratio of 8, okay? So we just have an 8. There's no label on that. Because what did we just find out then? That the new cube got how many times bigger?
8.
8 times bigger. So that means how many of those old cubes would fit in it?
8.
8. Yeah. And Julia was right all along. We did not have to make this quite so hard. Scale factor. And I'm going to put that in parentheses so we know we meet all the words. Scale factor cubed. 2 times 2 times 2, and that equals 8. So our sentence answer for this one would be what? How many of the original cubes would fit inside the new cube? 8. So you got somewhere to write a sentence yet? Okay. So I'm going to have to do mine up above here. 8. Oh, we're going to have to use the word since it starts the sentence here. Okay. 8 of the old cubes, or original, we use the word old because it's shorter. 8 of the old cubes would fit inside the new cube. Eight of the old or the original cubes would fit inside the new. So where do you think your reasoning went wrong, Noah? Do you think really 8 of these would fit on a layer? 8 of the old ones would fit on a layer in the new one? They're 4 by 4 by 4 going into an 8 by 8 by 8. How many would fit in a layer? How many? On a bottom layer, on a row.
4.
4 of them. How many rows would there be? Only 2, because that first row is going to be 4 inches high. The second row would be another 4 inches high. So altogether there'd be 8 cubes. Okay, so this one was. It seems like there should be a lot more, but that 4 is taking up 4 inches, 4 inches, 4 inches, 4 inches. Okay, so there's only 4 of them in a layer. 4 inches up, we only have another 4 inches for another layer. So there's 4 more in that layer. 4 times 2. Okay, let's do number 9, a cylinder. Is a cylinder 3-dimensional?
Yes.
Give me an example of a cylinder in our everyday life. A can, yeah. Pop can, soup can, whatever it is. Okay, a cylinder has a radius of 8 centimeters and a height of 14 centimeters. Each dimension of the cylinder is multiplied by 1/2 to form a new cylinder. Should we get a bigger cylinder or smaller than?
Smaller.
Smaller, because that's between 0 and 1. How would the ratio of the volumes compare to the ratio of the corresponding dimensions? Or in other words, I'm going to say let's find the ratio of the volumes. Anybody in here know how to find the volume of a cylinder? How do you? Okay, how do you? Devante?
Isn't that like pi times radius squared?
That's going to do one thing.
Or that's sphere?
No, that's not a
We know
sphere,
some-
that is a circle. Pi times radius squared is finding the area of a circle, but that's not going to help us. That's not the completeness of finding a volume of a cylinder. Cody?
Pi times radius cubed.
No. Do we really have to know how to find the volume, do you think? Does it matter?
No.
We know a shortcut. What's our shortcut?
The scale factor.
The scale factor cubed. You know what? Let's just, the ratio of volume, let's write this down. Ratio of volumes, let's write it in words first, equals scale factor cubed. Who cares what the volume of those cylinders are? And by the way, it's 2 pi r, or excuse me, it's pi r squared h. Let's find the area of the base, take it times the height of the cylinder, pi r squared h. But we don't need to do that. Because here's what we're going to do. We're going to find the ratio of volumes by taking the scale factor times itself 3 times. So our ratio of volumes is going to be what times what times what? What do we have to do? What's our scale factor? 1/2. 1/2 times 1/2 times 1/2. So the ratio of volumes is what that should say. So our ratio of volumes, one more time, we're going to write that, ratio of volumes equals what's a half times a half times a half?
1/8.
1/8. 1 times 1 times 1 upstairs is 1. 2 times 2 times 2 downstairs is 8. Our ratio of volumes is 1/8. So here's what we're going to say instead of how it says, how would the ratio of volumes compare to the ratio of corresponding dimensions? We're going to say the new cylinder would be, how would it compare in size? How would the new cylinder?
1/8 smaller.
It would be 1/8 the size. So in other words, 8 of the new ones would fit into the original or the old. So the new cylinder would be 1/8 the size of the old cylinder. 8 of the new ones this time would fit inside the old one. Before we were talking about how many old fit in the new one, they got larger. This got smaller. So we have to talk about how many of the new ones would fit inside the old one. 8 of them would, because it's 1/8 the size of it. Okay, one last one. We have a cone. Is a cone three-dimensional?
Yes.
Okay, it has a volume of 36 pi centimeters cubed, and every dimension is multiplied by a scale factor to form a new one. They don't tell us what the scale factor is. But they tell us the new cone has a volume of 972 pi centimeters cubed. What is the scale factor used? Julia?
Just divide 972 by 36.
Yeah, we'd have to put the new over the old. So we're going to put 972 pi. And by the way, we could put the centimeters cubed also, but we're going to see what's going to happen. 36 pi centimeters cubed. Does anything cancel out here?
Pi.
Pi's do. Centimeters cubed do. So we're going to get our ratio of volumes right now. What is our ratio of volumes?
972 over 36.
Yeah, whatever 972 over 36 is. 27? Okay. We just found our ratio of volumes, okay? So this is, where you need to put that in your notes so you know that's what you found. Is that what they wanted us to give? Are we done? Okay. Ratio of volumes is 27, but is that what they asked us for? Jossie says no. What were they asking us for then? Scale factor. How do we get the scale factor?
You divide 27 by 3.
Ooh, you think so? You think you divide by 3? Okay, let's set up our little thing that we said we already know. The ratio of volumes equals the scale factor cubed. We write that enough times, we'll get this. The ratio of volumes equals the scale factor cubed. That means we just found the ratio of volumes. We can put 27 in place of that. Scale factor, we don't know what it is, but we know what cubing means. It means take something times itself. It has to be a factor 3 times. So we're really looking for what times what times what. What times itself 3 times is 27. 3 is, so 3 times 3 is
9.
9, and 9 times 3 is 27. Yeah. So did we just find the scale factor? What is it? Yeah, the scale factor is 3. Okay. That's volumes. Anybody have questions on what happens to volumes when you change the dimensions of a three-dimensional object? Okay, then using yesterday's notes, along with today's,